Okay, so this is our chapter 6, lecture number 1, and we're looking at Avogadro's number and the mole and mass relationships. Oh, I gotta grab my writing pad. I'm not prepared. Okay, here it is. All right, so now we're revisiting a little bit of the periodic table. Hang on just a second. Okay, so previously when we introduced the periodic table, we looked at the periodic table and we said something about mass. And we did say that geez, stop it. That if we look on the periodic table, that this little number under here was the mass, or the average mass of each atom, weighted for abundance. Do you guys remember that? Does that sound familiar? Not that each atom weighs that much, because you have different isotopes, right? But the average mass weighted for abundance came out to be something like that. So this is going to be really frustrating. I have to draw with my mouse for a minute here. So we can say that one He atom, on average, weighted for the abundance of particular isotopes, we could say that the average He atom weighs 4.002. Do you guys remember what the units were for that? AMU, exactly, yes, atomic mass units. And this was kind of a unit that was created because they didn't know exactly what that mass meant. They just knew it was relative. So they said hydrogen is the smallest mass, so we're going to give it 1 atomic mass unit, and then helium's the next, and we find that helium's 4 times heavier than hydrogen, so helium gets about 4 atomic mass units, and carbon's 12, gets 12 atomic mass units, but they didn't know what the atomic mass unit meant necessarily. But they did know that individual atoms then, on average, would have these particular masses. And that's kind of important because when we're talking about reactions, we know that they always react in whole number ratios because you can't have like half of an atom. And so when we're running reactions, we want to know how many atoms we're working with so that my reactions can occur in the most efficient way. So let's say, for instance, that I was making a drug to cure cancer. And I knew that that drug would need 4 hydrogen atoms and 3 carbon atoms. Then I would want to make sure that I had the right mass of hydrogen atoms and the right mass of carbon atoms to put that together to make my drug. That's kind of a simple analogy, but I hope that that makes sense. The bottom line being that we know that these react in whole number ratios. We want to use the mass to predict how many atoms there are so that I can react them in whole number ratios. Does that make sense? You guys kind of with me there? This is why we care about mass. Okay, excellent. Okay. The only problem with counting carbon atoms and counting hydrogen atoms by looking at mass is that there is an astonishingly large number of carbon atoms in any mass that we could actually weigh. So like a gram of carbon atoms or a gram of hydrogen atoms has so many atoms that we can't even really fathom. I mean, we can count it, but our brains can't really comprehend the staggering number, or in other words, the staggering size, how small these things are and how many it takes to get an amount that we could actually measure. So scientists came up with a clever idea. And here's what they said. They said, look, we know that one hydrogen atom weighs about 1 atomic mass unit, and one helium atom weighs about 4 atomic mass units. And these were just relative anyways, right? So if we had 10 of each, 10 H atoms, how much would that weigh? Right, this would weigh 10 atomic mass units because it would be 10 times 1. And what about 10 helium atoms? What would that weigh? It's going to be 10 times 4, right? We just multiply both sides by 10. And this is going to be about 40 atomic mass units. Right, so this relative 1-to-4 ratio is always preserved if we have the same number of atoms, right? Because if I had 1 and 1, it was 1-to-4. If I had 10 and 10, it's still going to be a ratio of 1-to-4. That relative mass doesn't change if I have the same number of atoms, right? So for instance, if I had 1,000 H atoms, H's, how much would that weigh versus 1,000 heliums? 1,000 atomic mass units. Versus 4,000. Perfect. Now we're getting to the range of proteins. Proteins are huge. They can easily weigh 1,000 atomic mass units, which is kind of astonishing to me. Okay, but I hope you guys see that so long as we have the same number of atoms, then the mass ratio will always be the same, 1-to-4, 1-to-4, because it was always relative in the first place. Everybody understand that? Excellent. Okay, good. So somebody really clever sat down and said, you know what would be really cool? Let's just discover whatever number it is. And we don't need to know it right up. We can just calculate it maybe later. But let's say I have X H atoms and the same number of helium atoms. And let's just define X or discover X such that X weighs 1 gram. Or I should say 1.008 grams. That's the actual mass listed here, 1.008. If I had a certain number of H atoms that weighed 1.008 grams, how much would that same number of helium atoms weigh? Everybody agree with Caleb? Yeah, about 4 grams. Because it's the same relative number, so the mass is going to be same relative masses. Wouldn't that be convenient? Because then we could use the number on the periodic table. It could mean 2 things. It could mean that one carbon atom weighs 12.01 atomic mass units. It could also mean that one batch of carbon atoms weighs 12.01 grams. And so these numbers kind of do double duty. Atomic mass units weren't terribly useful anyways, because nobody has a scale that weighs atomic mass units, but then we could just use these numbers for grams, and we wouldn't have to come up with another number. Wouldn't that be awesome? So convenient. All right, so this number, the question then is, how many hydrogen atoms does it take to make the mass equal in grams to the number that it was in atomic mass units? That's the next question. Anybody know what that number is? How many atoms it takes to do that? It's a lot. It's a gajillion. Not a gajillion. I'm sure that they actually have a metric prefix for it, but I am not sure that I know what it is. Travis was typing. I thought he was going to tell me what it was. I can tell you, but if you guys could tell me, that's even better. It's a lot. The question was, how many atoms does it take to get 1.008 grams worth of hydrogen atoms? And Philip's right on. It's 6.022 times 10 raised to the 23rd, I think. The 23rd? Six 6.022 times 10 to the 23rd. Yeah, 23rd. Yeah, no, you're good. This is a number. There are no units associated with it because this is what we might call a batch, that it's just a number value. For instance, a dozen is 12 and a score is 20, and this batch is 6.022 times 10 to the 23rd. We're going to call this batch a mole. You've heard of the mole before, I'm sure, but now you know what it is. A mole is just a batch, like a dozen, or a googol, or a score, that represents this many of anything. And this number is just so ginormous. I mean, you can't even begin to fathom. I mean, we already have a hard time picturing what a million means or what a trillion means for scale, and that's only like 9 zeros. And here there's going to be literally like 23 zeros, okay? There's going to be a lot. I mean, we could write it out. We could say 1 mole of anything is, let's see, 6. There's 1, 2, 3, 0, 4, 5, 6, 7, 8, 9, 10, 11, 12, 23 of anything. It's just enormous. It's beyond comprehension almost. Okay. So it's a lot. And we could never count individual atoms, although it's important to know the ratios of individual atoms because that's how they react. We could never count individual atoms. They're just far too tiny. So instead, we're going to count batches. We're going to count moles of atoms because we're working with so many, it will make more sense for us to use these batches rather than individual atoms. Okay. So then, if we're looking at our periodic table, you guys can see that 1 mole of carbon atoms would weigh how much? 12.01. 12.01 what? Grams, right? 1 carbon atom itself would be 12.01 atomic mass units. 1 mole of carbon atoms is going to weigh 12.01 grams. What about 1 mole of sulfur atoms? How much would that weigh? Perfect, 32.07 grams. Do you guys feel pretty good about this? And we determined that 1 mole of hydrogen would weigh what? we always start you out easy, huh? Perfect. 1.008 grams. Now the next question you guys are going to have is how many digits do I really want? I'll usually cut you off at about the hundredths place, so 2 digits past the decimal is really sufficient. But this is the periodic table you'll have on the exam, so you should probably, if at all possible, use this one while you're doing your homework. Okay, so that makes sense. Let's take it just another step further. What if I had a molecule? Let's say I had a molecule of CH4. One CH4 molecule would weigh how much? And what about a mole of CH4? How much would that weigh? How would you determine that? Is that extra complicated? Oh, close. Watch out, Robin, because I've got 1 carbon and 4 hydrogen atoms. Yep, so Danny's right. You just take the mass of carbon, which is 12.01, and add 4 times the mass of each hydrogen atom, or you add 1.008 4 times. And if you do that, you should get 16.042 grams, it looks like, about. Or about, I'll just say 16 grams. So that's 12 plus 4, about 16 grams. Or sorry, oh, excuse me. 1 molecule would weigh 16 atomic mass units. A mole would weigh 16 grams. Perfect. Do you guys follow this? What about 1 mole? Let's do one more. 1 mole of CS2. Oh, perfect. About 76.15, 76.16. If it was a molecule, that would be atomic mass units. Since I asked for the mole, then it's going to be grams. So about 76.2 grams or so. Okay. So if we go to our in-class activity sheet, 6.1, the first section is to calculate, we call this the molar mass, or that is the mass of 1 mole. For each of the substances. And you could say 1 mole of P4O6 weighs X number of grams. You calculate this out. I'll do this one with you. Note there's 4 phosphoruses and 6 oxygen atoms. So you're going to have to say 4 times the mass of each phosphorus, which is 31. Let's see, where was I? 30.97. 30.97 plus the mass of 6 oxygen atoms, which is 15.9994. And if I add all that up together, just pull out our trusty calculators. Here we go. 4 times 30.97 plus 6 times 15.9994 gives me a net mass of 219.88. 219.88 grams. So I could say 1 mole of this equals 219.88 grams. Or another way to show this is if we divide both sides by 1 mole, then we find out that P4O6 is 219.88 grams per mole. Grams per mole. That's the number of grams per mole. Do you guys see what I did there when I reported that number? So 2 valid ways to report your answers. You could just say 1 mole equals that much. If I divide both sides by 1 mole, then I get the mass in molar mass, which is units of grams per mole. Did I make a mistake? I could have. 4 times 30.97 plus 6 times Nope, I'm still getting the same number, just off by 1. Not sure why. Anyways, let's do just a few of these together. See if you guys feel comfortable with them. Let me have you guys do this one. Copper 2 nitrate. What would the molar mass of copper 2 nitrate be? Make sure to pull out your periodic tables. Oh, great question. Megan Garza wants to know why I named this copper 2 nitrate. It's because of the charge. Well, yes, since the charge on the nitrate is -1 and there are 2 of them, then I know the charge on the copper must be +2. And so therefore I have to name it as copper 2. So I'm always telling you the charge if it's a transition metal. Now that's a great question because naming ionic compounds with transition metals, that is with this kind of a Roman numeral system, is what was the most commonly missed questions on the exam. So, and it's still fair game for me to ask you questions like that. So I'm glad. Okay, Shauna Meredith and Caleb came up with 2 different answers. Can I have a tiebreaker? Somebody else to weigh in here? We're going to take the mass of 1 copper atom plus the mass of 2 nitrogen atoms plus the mass of 6 oxygen atoms, right? Denny's agreeing with Shauna Meredith. Make sure that when you've got a subscript here outside of parentheses that you're multiplying it through, right? So copper plus 2 nitrogens plus 6 oxygens. We know the oxygen is about 16. Nitrogen is about 14. And copper is, let's see, 63.5. So 63.5. So if I've just done these quick kind of roundings, plus 2 times 14 plus 6 times 16, 187.5. Perfect. Yes. Okay, that's we're all getting the same answer. 187.56 or 57 grams. Okay, so this is then going to be 187.56 grams per mole. Perfect. In this case, I just did a really rough rounding to estimate which one of you guys looked like you were right. So I got 187.5, which was very close to you guys' 187.56. So I knew that that was going to be the right answer. The most precise rounding rules are going to be use all the digits given and then round at the very end, just to like 2 digits past the decimal. And that will be sufficient for the purposes of our class, if that makes sense. Okay, you guys want to do one more, or do you feel pretty good about these? 1 or 2 more? Nobody's brave enough to say whether they're ready to move on or whether they'd like. Okay, more please. Okay, let's do NaOH and NH42SO4. Each of you guys can pick one of those that you want to do. Try that out and report your results. Okay, Robin and Danny are agreeing on sodium hydroxide. That's good news. Excellent. 3 agreements for sodium hydroxide. Anybody else try ammonium sulfate? Uh-oh, we've got 3 different answers for ammonium sulfate. 2 different, yeah. Shauna, Meredith, and Brooks are agreeing. Let's look at this one. So ammonium, note you're going to have to multiply this through, right? So how many nitrogen atoms do we have in ammonium sulfate? 2 nitrogens. How many hydrogen atoms? 8 hydrogen atoms. Good. How many sulfurs? 1 sulfur. And how many oxygens? 4 oxygens. Okay. So if each oxygen is about 16 grams per mole, and each sulfur is about 32 grams per mole, each hydrogen is about 1 gram per mole, and each nitrogen is about 14 grams per mole, then we can say 2 times 14 plus 1 times 8 plus 32 times 1 plus 16 times 4 gets me about 132. Excellent. So yeah, so the most common mistakes we're going to see there are going to occur when we forget to multiply through and tell us that we've got 2 nitrogens and 8 hydrogens. But you guys came up with what, 132.14? 132.14 grams per mole. Okay, so this is just a matter of looking up the numbers on the periodic table, multiplying them by the amount of that atom that you have, and adding it up. You will have a calculator on this upcoming exam, so I think you guys can do that. No problem. No problem. So it's just a matter of becoming really familiar with your periodic table, making sure that you can multiply through so you know how many of each atoms there are and adding it up. Okay, we're going to actually have lots more practice for this for the next couple sections. So let's move on because we will include this. You are going to need to be able to do this in order to do the next few sections. So make sure that you've got that. Oh, just a little aside, this number, this batch, this number in particular is called Avogadro's number. Not because he discovered it, but because he was popular enough that they decided to name it after him. So Avogadro's number is this. You don't have to memorize it. I will give you this conversion on an exam. We'll only have a couple problems on the homework, maybe one on the exam about this number. And then after that, we're not going to worry about knowing exactly how many atoms are in that number as much as we're going to worry about being able to work with the mole. But that is Avogadro's number. As a result, we also get a special holiday. Chemists came up with Mole Day because mathematicians had Pi Day and we felt really left out. So we decided to make Mole Day our little holiday, which is on October 23rd. So it's coming up, guys. 10 days from now, October 23rd. specifically, especially celebrated at 6:02 a.m. and p.m. That's the mole day. We would have chosen June 2nd, but nobody's in school June 2nd, so it's not really useful for purposes of an educational holiday unless it's inside the school year. So October 23rd, guys, put it on your calendars. We should have a party. I don't see any laughs. Really need to have like you guys on microphone so I can hear you chuckle at my silly jokes here. But okay. You guys are funny. We should dress up. Do we have class on the 23rd? We could like dress up in preparation for Halloween. That would be fun. Let's see. Nope. 23rd is Thursday. Too bad. That's right. Chemistry nerds around the world will be celebrating. Could dress like a mole for Halloween. Okay. All right. So this is awesome because moles are great. Really, they are great because they help us convert from these numbers, which as atomic mass units weren't terribly useful, to something like grams, which is totally useful. So we like moles. But I hope it hasn't been totally lost on you. I hope you haven't been outside of dimensional analysis for so long that you don't recognize this is an equivalency that can now be used as a conversion factor. And so now we can do dimensional analysis all over again, but with moles and mass. Doesn't that sound like fun? Of course it does. Yay, dimensional analysis. Yay, okay. So let's let dimensional analysis. We determined that 1 mole of CH4 weighs 16 grams. Right now I'm just rounding up to 2 digits because the rest of the digits aren't important for what I'm talking about, right? 1 mole is 16 grams. So if I know that, maybe you guys can tell me if I have, let's see, 39.2 grams of CH4, could you guys tell me how many moles is that? Or if I told you that I had 0.56 moles of CH4, could you tell me how many grams that is? You guys could do both of this. It's dimensional analysis, so remember you're going to set this up to get rid of the units you don't want and to get the units you do want, okay? So, yeah, we'll do one first. It's okay. This is our conversion factor. This is our equivalency. If this equals that, we can use it to convert between grams and moles. So if I have grams and want moles, then great, I can convert from grams to moles. Or if I have moles and want grams, great, I can convert from moles to grams. So let's see here. Philip answered this last one. So let's check his work. He said, look, I was given 0.56 moles of CH4. And I don't want moles, I want grams. So I'm going to set this up to cancel out my moles and get grams on the top because that's what I asked for. So using this equivalency as a conversion factor, what can I put where so that my moles will cancel out and I'll be left with grams? Danny, figuring out the mass of 1 mole we just went over, yes. But using that to determine how many moles are in a different number of grams or how many grams are in a different number of moles, that's the next thing we're doing. Okay, so Janica says for this particular problem, we want grams on top and moles on the bottom, so they'll cancel. So my moles are here, 1 mole of CH4 on the bottom, and my grams are here, that is 16 grams. I should say it's 16 grams of CH4. Okay. So my moles of CH4 will cancel, and I'll be left with grams of CH4, and that's exactly what I asked for. Excellent. So I can stop, and all I have to do is multiply through. 0.56 multiplied by 16 gives me 8.96 grams of CH4. Excellent job, Philip. Great job. Excellent. What if I said I've got 39.2 grams of CH4? How many moles would that be? Let's do this together. We've got 39.2 grams of CH4. I don't want units of grams. Instead, I want units of moles. How can I get rid of the grams and get to moles? Jyotika says put the grams on the bottom, so they'll cancel. Okay, so here's 16 grams of CH4. And therefore, the moles go on top. That's the number of grams in 1 mole of CH4. And since 16 grams is the same as 1 mole, this value equals 1. I'm not changing the amount of CH4 I have, I'm just changing the units it's expressed in, because I converted from units of grams to units of moles. So how many moles is that? Somebody else should do it too, just to make sure that I'm doing it right, because I'm not perfect. You guys got that too? Excellent. Moles of CH4. And note here, by the way, when we're doing our dimensional analysis, at this point, because we're looking at moles and mass, every number value has a measurement unit that associates with it and an identity unit that associates with it that we should include in everything that we do, okay? Because grams of oxygen can't cancel out grams of CH4. But if we keep our number unit and our identity unit together, then we can be sure that we're going to get the right answer because we're following our units. Okay. Let's do just a few more and then we'll look at our in-class activity sheets. Okay. Let's say, for instance, I have say 0.295 grams of C6H12O6. And I want to know how many moles is that? What's the first thing I'm going to need to do to be able to answer this question? Perfect. Brooke says find the total weight or the molar mass of the C6H12O6. I think that's what Danny was saying, was figure out whatever this is. How many grams are in that? Okay. Yeah, or the atomic mass units, which is the same, because the atomic mass unit of one molecule is the same as the grams of 1 mole. That was this, right? This is our molar mass that we had to use to do this conversion in the first place, which is why we started this lecture by learning how to calculate molar mass. Okay, we can do that. We've done it before. So the molar mass of C6H12O6, we're going to be just a little bit sloppy here. 6 carbons that each weigh 12. By sloppy, I mean I'm rounding. Plus 12 hydrogens, which each weigh 1. Plus 6 oxygens, which each weigh 16. Gives me a total mass of, oh, Danny's already done it. Excellent, on top of it. 180, she didn't round hers off, so she has a more precise number. I'll use hers instead of mine. 180.156, or let's do 180.16 grams per mole for C6H12O6. Perfect. Excellent. Okay. So this is now a conversion factor that's going to get us between grams and moles. So let's see. I want moles. Moles is what I want. What should I do? How should I set this up so that I can get moles and get rid of my grams? Let's put, Megan, do you mean this one, our original? Because we want to end with moles on top, right? Yes, that's what you mean. So we could say, all right, I have 0.295 grams of C6H12O6. Now I want to get rid of grams. So, excellent. Danny says we're going to put this number on the bottom because that's where the grams are. She's right. 180.16 grams of C6H12O6 in every, that means the moles go on top, 1 mole of C6H12O6, which is perfect. That's what we wanted because that's what we're looking for is moles. So our grams cancel. Hooray! And when we divide 0.295 by 180.56, then we get 0. I believe that, 16374 moles. Or we could say 1.63 millimoles. We round it off here. Obviously, these are both the same answer, and I wouldn't make you choose between them on an exam, okay? But the milli means times 10 to the minus third, so we can move that over. It's another way of looking at it. You guys with me here? We did 0.295 divided by 180.16, and we got 1.64 millimoles as our answer. Excellent. Okay, let's do another one. Let's go the other direction. Let's say I want a total of 3.94 moles of magnesium hydroxide. If that's how much I want, then how many grams should I be weighing out to give me that many moles? Help me out here. What's the first step I'm going to need to be able to do? Molecular mass of, or molar mass of my magnesium hydroxide. Excellent. Okay, you guys do that because it's good practice. See if we all come up with the same answer. Caleb's got an answer. You guys agree with him? Looks like Brooks agrees. This was going to be the mass of magnesium plus 2 oxygens plus 2 hydrogens, right? And we're all agreeing that it's about 58.3 grams per mole. Excellent. Okay. So if I'm given moles and I want grams, and I have this conversion of grams per mole, how do you guys want me to set it up? And remember, there might be more than one correct way to set it up. So if you're watching this lecture and you think, I wouldn't have done it that way, I would have done it another way, So long as you get the same answer, you did it right. But how would you guys set it up? Okay, you guys have the right numbers in the right places, but I don't see your units, so I'm not sure that I would know that if I hadn't already gone through this myself, okay? In other words, you guys are saying, I have 58.3. I want grams, so let me just put this front and center. I'll put grams front and center. That comes grams per mole. And this is magnesium hydroxide. This is magnesium hydroxide. And then I can say, to get rid of moles, I'm going to multiply here, the 3.94 on top, so that my moles will cancel. So my moles, magnesium hydroxide cancel. And then the numbers, yes, it ends up being 58.3 times 3.94. Perfect. Yes, Megan, that's what I wanted to see. So you guys had the right answer, but I want you guys to see why, that your moles cancel. This is how you're going to set it up, so that in the future you'll be sure to know what to put where. So 58.3 times 3.94, I believe that it could be 29.08 grams. Everybody feel good about that? Excellent. Okay. So the moral of the story is, if we've got a substance and I give you grams and ask for moles, or if I have got a substance and I give you moles and ask for grams, you will start by calculating the molar mass, and then you're going to plug it in such that you eliminate the units you don't want and you get the units you do want. Just classic dimensional analysis style. Okay, excellent, excellent, excellent. Okay, let's look at this in-class activity sheet. Does that go for milligrams and kilograms as well? Well, yes, Danny, because this is just grams per mole, right? But at this point, you could convert from grams to milligrams if you needed to, once you have grams, or from grams to kilograms if you needed to. Or if you put milli on both sides, you would find 58.3 milligrams is 1 millimole, because the millis would cancel. Okay, let's look at this. So section 2 says, I'm giving you grams and I want to know moles. So grams, 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 grams. I want to know moles. Section 3 says, I'm giving you moles and I want to know grams. maybe once or twice, Megan. You guys can do that. You can do that. Okay, so I think you guys have enough tools to do section 2 and section 3. Okay, let's do just a couple of each section before we move on. We do want to make sure we get to everything, but I want to give you guys a good start, so I feel confident that I can just hand this to you and expect you to come to class on Wednesday with it completed, right? Which one of these would you like to do? Oh, let's do a milligrams one, just because Megan said please don't. That way we have a little bit of experience with it. So 125 milligrams of lithium carbonate, and I want to know the number of moles, right? So the first thing to do is to calculate the molar mass. And I'm going to do this for you just to save time, but you guys know how to do this. It's what you did in section 1. I'm just adding up 2 lithiums, 1 carbon, and 3 oxygen atoms. And I find that this weighs 73.89 grams per mole. Okay. Now, if I'm given milligrams and I want to get to moles, and I have a conversion between grams and moles, what should I do? Where should I start? There's kind of two directions I could come with this. I could either start with what I'm given, 125 milligrams, and try to get rid of that and get to moles, or I could start with the moles, because that's what I want in the end, put that front and center and try to get rid of the grams. Doesn't really matter. Which feels more comfortable to you guys? Would you rather start with 125 or the 73.89? Okay, let's start with 125. So 125 milligrams of lithium carbonate. Okay, now I don't want milligrams, I want moles. I do have one conversion unit that gets me to moles, but I have to have grams first. So the next question is there a convenient way for me to get from milligrams to grams so that I can then use that to get from grams to moles? How would I get from milligrams to grams? Perfect. Megan is right on. There are 1,000 milligrams in 1 gram. How should I insert that conversion factor here in order to cancel out the milligrams and get the grams? Excellent. I'm going to put 1,000 milligrams on the bottom and 1 gram on top. This is good for anything, but since I'm working with lithium carbonate, I'll just be consistent. Okay, so my milligrams of lithium carbonate canceled out. Okay, now I'm left with grams of lithium carbonate, and I want moles, so what do I do now? Excellent. Now again, we're going to put the 1 mole on top because that's what we want of Li2CO3. Notice I'm always leaving that identity information there. 73.89 grams on the bottom. And if I do that, then my grams of Li2CO3 get canceled out, and I'm left with moles. And that's what I wanted. So I know that I can be done with a setup, and all I have to do is plug it all in. So 125. Wait, Danny. We ended up putting 73.89 on the bottom, right, to cancel out my grams? Yeah. You had all of the right numbers. You just have to make sure that you have what's on the top should be on the top, what's on the bottom should be on the bottom. Because we had to put grams on the bottom to end up with moles on the top. So we should have 125 divided by 1,000 and then divided again by 73.89 grams. That looks right to me, Megan. 1 point, yep. Or 1.69 times 10 to the minus third mole, which is the same thing as 0.00169, right? Excellent. Megan was exactly right when she identified that the moment we were talking about grams, that I could throw milligrams or kilograms at you as well. I could even throw micrograms or nanograms at you if I really wanted to, but I might not be that mean. But so long as you know your metric conversions, which in fact you should still know your metric conversions, because I had you memorize them not because I was being cruel, but I had you memorize them for a reason because I wanted you to be able to use them for the rest of the semester. Okay. I want you to be really familiar with these and be able to use them. So when I throw milligrams, you're like, oh yeah, that's the same as grams. That's really easy. I can get the grams from there. And then this is the only really new thing that we're doing. Okay. Baby thanks test. Okay. Let's do one from section 3. Note, I think I told you guys, when you're doing your in-class activity sheet, strongly recommend in the margins, you just write down a description of what you're doing so that when you go back, you can solve that. So the description here would be to 1, find the molar mass. And then 2, use dimensional analysis to convert to moles. That's what we did, okay? And for part 3, our instructions, first we're gonna have to find the molar mass. So what's step 2 gonna be? Grams, yep, use dimensional analysis to convert to grams. Sorry if my handwriting here is exceptionally bad today. I'm using my mouse instead of my pad, so a little bit harder. Okay, but pretty much the same thing. And then how do we find the molar mass? That is exactly what this section was. We add together the individual masses of each atom in the molecule. Okay. So step 1 gave us the practice for what the first thing we were going to have to do for both of these sections. All right, so let's do 7.74 moles of sodium nitrate. And again, I'll do step 1 for you really quickly because I don't want to spend extra time on that as much as I want to make sure that we just get the concept here. Sodium nitrate is okay, hang on a second. So what is going on? Sodium nitrate is 85 grams per mole. You guys might like this better, because then you can actually see rather than having to read my scribble. So sodium nitrate is 85 grams per mole, and I have 7.74 moles of it. How am I going to set that up? Oh, Annie just went straight to the answer. And she got it right too. We said 7.74 moles NaNO3. And then to do this dimensional analysis style, we want grams on top. So we're going to leave 85 grams of NaNO3 on top. And then on the bottom, we're going to have 1 mole of NaNO3. When I add that all up together, or rather I should say when I multiply that through, I should have 657.9 grams of NaNO3 grams of NaNO3, because my moles canceled. Do you guys see? This is, I want to show you this because this is often what I've got on the keys, the in-class activity sheet. So if we're doing this on the discussion forums, this is essentially this setup here, but each section alone. Perfect. Yes. Caleb's almost perfect. I think that first number should be 7.74. Oh, no, you got it. Never mind. Okay, we're good. Okay. I'm going to let you guys practice this on your own and bring this first page completely done to class on Wednesday. Okay, I think you guys can do this. It's pretty straightforward. Again, first you find the molar mass, and then you're going to use differential analysis to cancel out the moles and to get to the grams that you want. Okay, and let's take a 5-minute break, and we'll start in on the next section.